right, last lecture before the midterm, and here I'm going to go through this stuff a little faster than I usually do, just because at this point I'm hoping that you have reviewed the Crash Course in Physics videos that I sent out to you last Monday. And so also, if you've had chemistry before, a lot of this will be familiar to you. But of course, it's not a prerequisite that you've had chemistry, so I'm going to go through this stuff as if you haven't seen it before, other than what you saw in the videos earlier this week. All right, so this is some selected topics from chapters 17 and 18. Depending on how far I get today, I'll make an announcement later on as to exactly what those sections will be for the midterm. All right, so first I wanted to take a look at temperature. And so, put simply, if an object has a certain amount of internal kinetic energy, that is related directly to the temperature. And this is true whether the substance is a solid, liquid, or a gas. Now for a gas, the internal energy, U, is equal to, if this is a diatomic gas at normal temperatures, diatomic means two molecules, or two atoms per molecule, like O2 gas, H2, N2, those are all diatomic gases. Then U is equal to, this would be for monatomic. The degrees of freedom go like 3/2 kT. Okay, where there is 1/2 kT for each degree of freedom, indicating that there are x, y, and z motions for the molecules in the gas. And so for the x motion, you'd have a 1/2 kT. For the y motion, you'd have a 1/2 kT. And for the z motion, you'd have a 1/2 kT. So this is essentially then the internal energy as it relates directly to the temperature. And that's equal to 1/2 times the mass of a given molecule times the average velocity, the average of the squares of the velocities. Okay, so this is the mean, the average of the mean square. Now this is different from the square of the mean. The average squared is 0 because the molecules have an average velocity of 0 in the x, y, and the z directions because there's as many molecules going in one direction as there is in another. But if you square it first and then take the average value, then that's not equal to 0, and that's an indication of the internal energy of the molecules in the gas. Okay, and so that being the case, we could figure out what the average velocity is for a molecule of air, let's say moving in this room right now, in terms of its temperature. Now the temperature here we'll be measuring in Kelvin. Where 273 Kelvin is equal to 0 degrees centigrade. And our degrees Fahrenheit is equal to 9/5 times our degrees centigrade plus 32. So for in Fahrenheit degrees, we want to convert to centigrade. We have to multiply the degrees centigrade by 9/5 and then add 32 to it. So if we're at 100 degrees centigrade, 9/5 times 100 is 180 plus 32 is 212. Or we could work in the reverse direction. If we know the degrees Fahrenheit, then we can solve this for degrees centigrade. And the increments of degrees Kelvin and degrees centigrade are the same, but they're shifted by 273. So we say then that 0 Kelvin is what we call the coldest you can get, or absolute zero. So here, the temperature then would be measured in Kelvin degrees. And here, this K value is what we call Boltzmann's constant. K is equal to 1.38 times 10 to the minus 23, and that's joules per molecule degree Kelvin. So this then connects in our internal energy to the average kinetic energy of a single molecule in the substance. So from this then, we could figure out what the typical velocity is for the molecules in a gas like air. Now for air, your mean or average value for the mass of a molecule of air assuming that we have 80% nitrogen gas and 20% oxygen in our atmosphere, which isn't quite right, but it's close enough. Then this would be, if we wanted the mass of a nitrogen, then we would look at the periodic table. We would see that nitrogen has an atomic number of 14. So it would be 14 what we call atomic mass units, or 14 times 1.67 times 10 to the minus 27 kilograms. The mass of O2 would be, well, oxygen has an atomic weight of 16, so to be 2 times 16 is 32 times 1.67 times 10 to the minus 27. So this should be 2 times 14, sorry, that's 28. Because it's N2, 2 nitrogens. Here it's 2 oxygens, so that's 2 times 16 is 32. And with 80% nitrogen, 20% oxygen, we could write this as a weighted average of 0.8 times 28 times 1.67 times 10 to the minus 27, plus 0.2, 20% oxygen, so that's 32, times 1.67 times 10 to the minus 27. So that gives us 28.8 times 1.67 times 10 to the minus 27 kilograms. So this is the average mass of a molecule of air, taking into consideration that 80% of it is nitrogen and 20% of it is oxygen. So if we want to know then how fast a typical molecule of air is moving, we can solve this equation for V average squared, and then we take the square root of that. Okay, and so that becomes then the mean square square root, or the root mean square, RMS. Okay, so from that equation, then the square root of that is going to be equal to the square root of 3 kT over our average mass. And so here K takes the role of our gas constant R, if you've had chemistry before, where you're talking about the number of moles. But here, when we're dealing with numbers of molecules, instead of using our gas constant in units of joules per molecule degree, mole degree Kelvin, we're using our K value in terms of joules per molecule degree Kelvin. And so that's more what we do in a physics class where we're not so worried about moles. So VRMS then, a typical velocity of the molecules of air in this room, if T, let's say, is 300 Kelvin, or that would be, what, 27 degrees centigrade. We're looking at, maybe mid-70s, high 70s. 28 degrees centigrade is something like 80 degrees Fahrenheit. So that's typical for what's going on right now. These are pretty hot days, at least it is today. So in this room then, right now, this would be the square root of 3 times K, 1.38 times 10 to the minus 23 joules per molecule degree Kelvin times the temperature. That always has to be in degrees Kelvin, not in degrees centigrade or degrees Fahrenheit. And then we'll divide that by the average mass of an air molecule in kilograms, 28.8 times, this is the mass of a single proton or a neutron, roughly speaking, 1.67 times 10 to the minus 27 kilograms. And that gives us a value of about 498 meters per second. Okay, so that roughly double that is the number of miles per hour. So it's about a typical gas molecule in this room right now moving around, although it's not really going anywhere. This is going back and forth, bouncing around with average displacement that's equal to 0 because there's no wind in this room. But it's going faster than the speed of sound, 1,000 miles an hour. And so that is the reason why we feel that pressure. Because those molecules are bouncing off of our bodies, and that is exerting pressure on us from all directions. So we talked about that a little bit in our previous section on pressure in chapter 12. Okay? And so this then justifies it, yeah, okay, these molecules really are moving pretty fast. And so that average kinetic energy then relates directly to the temperature. And so once we know what the temperature is, we can figure out how fast the molecules are moving. Or if we know how fast the molecules are moving on the average, we can figure out what the temperature is. Okay, now is that a an average velocity, or is it a typical velocity? The answer is it's a typical velocity. If we plot the number of particles here versus the temperature in a gas, and on the horizontal axis here, what we'd have is the temperature. Let's do this versus the velocity. And this will be at a given temperature. This is the curve at a given temperature. This is called a Maxwell-Boltzmann distribution. And what it is, essentially, and this isn't perfectly symmetric, this should kind of increase up and then maybe drop off a little faster on this side. That this is a distribution of molecular velocities versus how many particles are at each of the individual velocities. Okay, so in other words, if you had a pool balls that were knocking each other all around on a table, some would be moving faster and some would be moving slower. But you could still figure out what the mean square of the velocities were, but there would be a spread because they wouldn't all be going the same speed at any given time. And so somewhere in here we would have VRMS, a little bit past the peak. Here we would have Vmax, which we could get by taking the derivative of this curve with respect to the velocity and then setting it equal to 0. That would give us the slope of that curve at that point. And then you could also talk about the most probable velocity. Now the most probable velocity is just gotten by looking at the area under the curve being equal on one side of the curve versus the other side. So the most probable would be the one in which at that velocity you'd have just as many particles that have a higher velocity essentially as you would that have a lower velocity in terms of a weighted average of them. And so all three of these, the most probable, the max, and the RMS, are right in that same ballpark in terms of velocities. And so the RMS velocity is the easiest one to calculate, but it is still could be considered to be a typical velocity. But that doesn't mean every molecule is moving at that speed. It just means that some are going to be moving faster, some are going to be moving slower, but when you average them all out, that's a typical speed for the molecules in a gas. Okay? And so this expression then for the internal energy, which gives rise to temperature, is derived in your textbook. I'm not going to do that here. But I would like you to know what that relationship is. And that was one that was also discussed in the crash course video. And so that will give you more information about that. And remember that I will ask you some concept questions, or even possibly a numerical question that comes straight out of the crash course videos. So be sure to look at those if you haven't looked at those yet. Okay, so this gives us a feeling then for what temperature really means. And anytime that we think in terms of temperature, we can think of the kinetic energy of the molecules in the gas. But changes in temperature give rise to heat. So changes in temperature then mean that the internal energy changes. And we call that change in internal energy heat. So temperature and heat are not the same thing, but heat can produce a difference in temperature. So what is heat? Well, it's just an expression for the amount of energy that can be transferred between two substances. So it's related to the mass of the substance, the specific heat of the substance, which is discussed in the video before. And the change in temperature of the substance. Okay, and so we write then the heat Q as mc delta T. Okay, so this is the heat required to cause a temperature change, delta T, of an amount of mass m that has a specific heat C. Okay, so C then is what we'll call the specific heat. M is what we'll call the mass. The change in temperature is what we're calling here delta T. Okay, and so if the change in temperature is positive, then Q is positive. And so Q greater than 0 then, or the delta T that's greater than 0, means that heat enters the system. However, if Q is less than 0, that means that heat leaves the system. Okay, so if heat is leaving the system, it cools off. That means the change in temperature is negative, because T final then is going to be, if this thing is cooling off, T final will be less than T initial. Then T final minus T initial would be negative. Okay. And so, although heat and temperature are related, they're not the same thing. And so if the temperature changes then in a gas, that means that the average speed of the molecules changes too. Okay, and so the average speed of the molecules is going to go down if an object is cooling off. That means that it's losing some of its energy. It means it's losing some of its kinetic energy. Okay, and vice versa. If heat enters the system, then the average speed of the molecules goes up, and associated with that, the temperature goes up. Now, we're familiar with the specific heat for water, probably. That's 1 calorie per gram degree centigrade. But these are the wrong units for the kind of problem that we'll normally be solving in this class. A calorie is a unit of heat, but it's equal to 4.19 joules. Okay, and so joules is a more preferred unit of measurement for energy. And so in this case then, it's the energy that's associated with making the molecules move faster or slower. Okay, and so I'd want to convert calories to joules. I want to convert grams to kilograms. So if I do that, I've got 4.19 joules per calorie. And then I've got 10 to the 3 grams per kilogram. So that gives me 4,190 joules per kilogram degrees centigrade. That's the specific heat for water. So what does that mean again? Well, that means that 4,190 joules are needed to raise 1 kilogram of water by 1 degree centigrade. And so that's the definition then for specific heat. And so if it has a high specific heat, it means it's hard to change its temperature. It takes more energy to do it. If it's a lower specific heat, as was mentioned in the video, then that means that it's easier to change its temperature, because if for a given value of the heat that enters the system, if the specific heat is lower, then the change in temperature is higher. Whereas if the specific heat, like for example for water, is higher, then typically the change in temperature will be lower. Okay, for a given value of heat that might enter the system. And so let's take a look at this then with an example. Let's say that we have a bullet, and that bullet moves with a velocity of 10 to the 3 meters per second and has a specific heat that is equal to, in this case, let's make it 5 times the specific heat for water. Or for this problem, then, that would be 5 times 4190 joules per kilogram degree centigrade. Let's say that this bullet embeds itself in a block, and so the final velocity is 0. And let's say that we're also told that 40% of the heat that is released by the bullet goes into changing the temperature of the bullet. And let's say the bullet's initial temperature, when it's out here, is 40 degrees centigrade. Let's find the final temperature of the bullet. Okay, now I'm not talking necessarily about the temperature of the block here, because the block may be getting another 40% of the kinetic energy, and then maybe 20% is going into sound waves and other deformations and things that aren't directly related to heat. Or maybe the air is absorbing some of the heat. But let's just say this is right, that 40% of the kinetic energy goes into heating the bullet. Then, what we could do is we could write our expression then as, well, in this case, the kinetic energy is going to be equal to 1/2 mv squared, okay, where v is the velocity of the bullet, and m is the mass of the bullet. And so that kinetic energy then times 0.4 is going to equal the heat. Okay. So this is from the statement that 40% of the kinetic energy goes into heating up the bullet. So it's just like a word problem where you're kind of writing the equation from the way that the sentence is written. Right? So we could then, we say, well, wait a minute, we don't even know what the mass is. Well, it turns out if we just want the final temperature, then the mass is going to cancel, which means the result won't depend on the mass. So we'd have 0.4 times 1/2 mv squared equals mc delta t. Okay, so that's what we have then. And the masses cancel out, so the result then would be independent of the mass for this particular example. And so we could write this as delta t equals 0.4 v squared over 2c. Okay. And so here we've got the 2, and then we bring the c down, and so we're just solving this for delta t. Now you could write delta t as t final minus t initial, but let's do that at the end. So in other words, let's just find the change in the temperature first, and then we'll find t final from delta t is t final minus t initial. Okay, so delta t then is going to be 0.4 times 10 to the 3 squared, meters per second squared, divided by 2 times c. Now the specific heat we were told is 5 times the specific heat for water. So that's 5 times 4190 joules per kilogram degrees centigrade. so that gives us 9.5 degrees. Okay, and that would be either degrees centigrade or degrees Kelvin. Let me just run that through one more time. That's good. And so T final then would be T initial plus delta T. And so that would be, we started out with the temperature of the bullet at 40 degrees. Why was it so hot to begin with? Well, because it was fired out of a gun. Okay? So that's going to heat up the bullet. It's going to be experiencing a big explosion, and then it's going to feel friction as it moves through the barrel. And so we'll just assume that it starts out at a pretty high temperature. And then we'll add 9.5 degrees centigrade to it. And so that would be 49.5 degrees centigrade. Okay, so that would be T final. Okay, now you might wonder here, well, I said before that you need to use degrees Kelvin. And so why am I using degrees centigrade? Well, an increment of degrees centigrade is the same as an increment of degree Kelvin. So a change of 9.5 degrees centigrade is the same as a change in 9.5 degrees Kelvin. So I could have just as easily converted this to 40 plus 273 and then added 9.5 to that, and that would still be correct. But for temperatures that are around normal room temperatures, the numbers are a little more natural if we use degrees centigrade. And we'll notice over here in this equation, Q equals mc delta T, that it's a change in temperature and not a temperature itself. Okay, so if we're talking about just temperature, then it's got to be degrees Kelvin. But if we're talking about a change in temperature, then that could be degrees centigrade or degrees Kelvin. So either one will work for a change. But for an absolute temperature, like what we had in that previous example of the RMS velocity, you're stuck using degrees Kelvin. You have to use it no matter what. Okay, so this is an example then of how we can have some form of energy, for example kinetic energy, that can turn into heat energy, or at least some of it can turn into heat energy. And so in our previous examples, this was energy that was just lost from the system. Okay, it was gone. You know, but now we're seeing that, okay, well, we actually can still measure this energy, and it has a meaning in terms of heat. And so is heat always just wasted energy? And the answer is no. What if you wanted to make an electric heater? Then you would be using that energy that's lost and turning that into something useful that you could use to heat up your house. So, and also heat engines are used, for example, in cars. You know, a car is a heat engine too. And so there are ways of making useful, taking useful advantage of the energy that's lost into the internal motions of the molecules in the gas. So that is the kind of thing that we're looking at here. All right, so next what I wanted to do is look at an example of changes in temperature that cause a expansion of the material. Okay, so this is called thermal expansion. Now, in thermal expansion, if you heat an object up, in other words, if you add heat to it to change its temperature, this is going to cause a change in the length of the object. So heat is absorbed by the object, and the heat causes a change in temperature, as we saw before. But the change in temperature results in a change in length. In a one-dimensional problem like this, we can say that the total length, L total, is equal to L naught plus delta L, where delta L is the change in length caused by the object's change in temperature. So delta L then can be written as alpha times L naught times delta T, where this is the change in length alpha is called our coefficient of linear expansion. And so this is a property of the substance that we're looking at, but also property of temperature. Alpha can change with temperature. So it's a function of the material and in general also the temperature. Now we'll assume for small temperature changes that alpha doesn't change much with temperature. But if you're going to do this more accurately, you also need to include the temperature dependence for alpha. L naught is the original length of the object before it was heated. At T equals T naught. Okay, so that's the initial temperature. And delta T is the temperature change, as we saw before. That's T final minus T initial. So this must have absorbed some heat in order to have changed its temperature. And so in the process of it absorbing heat, it also can change its length. Now why does that happen? Well, even in a solid, this is going to occur because the molecules are vibrating back and forth that are associated with attractions between negatives and positives inside of the material. But as they start to vibrate back and forth, they start capturing more effective volume. And so one pushes against the next, one pushes against the next, and so they all kind of move a little more and they push on each other, and that causes the whole substance to expand a little, not a lot. And so here I'm greatly exaggerating how much it would actually expand. But that's not to say that even though it might only expand a little bit, that there aren't a lot of thermal stresses. You can get hundreds of thousands of newtons worth of thermal stress, even if you have say a 0.001% change in length. You can still get hundreds of thousands of newtons exerted. And so this is enough then, say, with a train track to cause the train track to buckle. And so those forces then will not be denied once they get going. And so this is why we have to adjust to the fact that objects are going to have this natural tendency to expand a little bit. And so that can affect the mechanical operation of our system. So in this next example, let's take a look at railroad tracks, in which the alpha value for this problem, let's say, is 10 to the minus 6, and that would have units of 1 over degrees centigrade for the steel in the track. Now, this number is just an easy number for me to work with, and it's not something that I looked up in a handbook of chemistry and physics. Okay, so this is not the correct value for most forms of steel, but it's still in the right ballpark, and it makes it easier to do the calculation. So let's say that each length of track has a length here that's equal to, let's say, 100 meters. That's L naught. And then this next length of track has a length of 100 meters. Let's find the spacing between the track that will allow for a temperature change of 40 degrees. Degrees centigrade. Okay, and so L naught then would be the length at the initial temperature, and then that will expand on one side to delta L over 2. Why? Because it can expand just as easily in the other direction by delta L over 2. And so that means that the next track over here will also expand by delta L over 2. And so that'll make the total gap between the tracks delta L. Because you have a delta L over 2 and a delta L over 2 for each of the individual tracks. And so that means you have to accommodate twice that gap. Or that's just the delta L that we're looking at in this calculation, this equation. So we can write here delta L then would be alpha 10 to the minus 6 per degree centigrade times L naught 100 meters times delta T 40 degrees centigrade. Okay, so that'll be, well, this is 10 to the minus 4 times 40, and so that would be 4 times 10 to the minus 3 meters, or that would be 4 millimeters. Okay, so for a alpha value that was 10 to the minus 6, we would have to separate the tracks by 4 millimeters in order to accommodate this. And so that doesn't seem like very much. But if you just made it a solid stretch of track, hundreds of miles long, and you have this 4 millimeters expansion that's happening every 100 meters or so, that can easily generate enough thermal stress to cause the track to bow. Okay, and to accommodate that stress, and so as the track starts to change its shape, then the train derails. Okay, so this is an important consideration then. And also in bridges, I invite you to take a look at how they handle that kind of expansion in a large structure, which is in the video that I recommended to you on temperature. So if we're talking about volume expansion, that's equal to beta times V naught times delta T, where beta, if it's what we call a well-behaved homogeneous isotropic substance, beta is equal to 3 alpha. Okay, so then this is the change in the volume of an object that is a three-dimensional object, rather than talking about a change in the length. Okay, and so you could have, for example, a cylinder that's made out of the same metal, and we could ask what delta T will produce a 1% increase in volume. If alpha is 10 to the minus 6 per degree centigrade. And so here then, it may not seem like we have enough information to solve for the change in temperature. It will produce a 1 degree increase in the volume. But a 1 degree increase, or 1%, sorry, increase in the volume for this problem is just the same thing as saying that delta V is 0.01 times V naught. Because V total is going to be equal to V naught plus delta V. And if we're looking for a 1% increase, that would be 1.01 times V naught. So therefore, delta V is 0.01 times V naught. And so that means that we can write everything in terms of, here, in terms of alpha and V naught. And we already know alpha. So we have 0.01 V naught equals 3 alpha, which is beta, 3 times 10 to the minus 6 per degree centigrade, times V naught times delta T. Cancel out the V naught, so we didn't need to know what the height was or the radius. We just wanted to expand by 1%. And so that gives us a delta T that's equal to 0.01 divided by 3 times 10 to the minus 6. So that's going to turn out to be a pretty big temperature. That gives us 3,333 degrees centigrade. A change in temperature that is so huge that the metal will melt before this ever happens. And also our assumption that alpha is constant will be blown out of the water because of the huge temperature change that alpha is experiencing. And so this is not possible. Why did I do an example? It's not possible. Well, to show you how small these changes have to be. Okay, so for this to be a reasonable change in temperature, I'd have to be looking at, well, if I cut this down by a factor of here, if I make this 1/100th of 1%, then this would be 33.3 degrees centigrade. So that's a little more reasonable. So that's the kind of change in volume that we're looking at, is 1/100th of a percent, not 1%. And then that would cut this factor down by a factor of 100 to 33 degrees centigrade. Then the alpha, you might make the argument, is constant over that temperature range. Okay, so this shows us then how small the variations need to be. And so this tells us here that the fractional change in volume can't get that big. But maybe 0.01%. That would be a more reasonable value that would give rise to a result that we could measure. Okay, so what would happen if you filled up a glass of water with water and the alpha of the water is greater than the alpha for the glass? and then you heat up both of them. We could ask, will the water overflow? Will the water stay the same? Or will the water level drop? Well, first we have to understand that if you have a hole in something, the hole grows just as fast as if there were, in this case, glass in there. So this glass container then has a big hole in it, right? Because it's like a hollow cylinder, at least, okay, and although it's enclosed on the bottom, you can think of this as just being a big hole. But that hole will grow just as fast as if this thing were made out of solid glass. And so the glass then, when it expands, it takes the hole along for the ride. So the hole doesn't get smaller, the hole gets bigger. Okay? And so given that that's the case, and the alpha for the glass is less than the alpha for the water, that tells us that the water will expand faster than the glass, because the delta V is going to be 3 alpha times V naught times delta T. They both have the hole in the water and the actual amount of water that's in that hole are the same in volume. And so the change in volume of the water will be greater than the change in the volume of the hole in the glass. Or you could also do this with, say, a hole in a piece of steel. If this length here is L naught and this diameter of the hole is D naught, then as the metal expands, the hole expands too. It gets just as big as if there were metal in the hole. Okay? And so the same thing is true here for the hole in the glass. That is not going to expand as fast as the water if alpha water is greater than alpha glass, and so therefore it'll overflow. On the other hand though, if the alpha for the water were less, if the glass could expand more than the water, then the water level would drop, okay? Because then the hole would get bigger at a rate that's bigger than how fast the water is expanding. So the water level will drop. And so these are conceptual ideas that can be related directly to numerical examples. And I gave you one that is like that in the Mastering Physics that you can look at. But what I'd like to do next is take a look at phase changes. So we're just kind of moving right along here through these different subjects. Each one is somewhat related to the previous one. We've got two principal kinds of phase changes we'll be looking at here. We have solid to liquid, or equivalently liquid to solid. So if we have something that's in a solid state, and we break apart those bonds by adding heat to the system, we can turn it into a liquid. Now for water, this takes a certain amount of energy. And so this is what we would call heat energy. And so if there's a constant phase, in other words, no phase change, then we've already seen that Q equals mc delta T. But if there's a phase change, then Q is equal to ml. Where m is the mass of the material, and L is the latent heat that is required to produce a phase change. So for the conversion of ice into water, we call the latent heat of fusion the constant that relates the heat that is required to make the phase change with the mass that we have. And so for water, this is 79 calories per gram. Or if we convert that to, if we convert grams to kilograms, we have 10 to the 3 grams per kilogram and 4.19 joules per calorie. This gives us 4190 times 79. Which is 3.3 times 10 to the 5. So for water, 3.31 10 to the 5 joules per kilogram. This means it takes 331,000 joules to melt 1 kilogram of ice at 0 degrees centigrade. Okay, so phase changes occur at constant temperature. And equivalently, temperature changes occur at constant phase. So you're doing one or the other, but you're not doing both at the same time, provided the material is in thermal equilibrium. Now, if you don't stir a bunch of ice that is melting to maintain thermal equilibrium, then you may have places where the temperature is changing and other places where you still have ice. Okay? But by stirring it, you maintain thermal equilibrium. And then these simpler equations will apply. It gets really complicated in a real life situation if you don't have thermal equilibrium. And so we like to look at either one or the other here, but not both at the same time. So if I were to, let's say, have a piece of ice, let's say that this piece of ice is at 0 degrees centigrade and it's 2 kilograms of ice. And then I ask then, well, how much heat do I need to turn it into 2 kilograms of water? At 0 degrees centigrade. So in other words, it's still at the same temperature. But what I would do then is I would just multiply the 2 kilograms by 3.31 times 10 to the 5 joules per kilogram. And that'll give me the joules. Notice that the m values, the kilograms, will cancel out of this equation. 2 kilograms times the latent heat, in this case the latent heat of fusion for water. And of course we're talking about water in a different phase state here. And so that would give us 6.62 times 10 to the 5 joules. Or if we were trying to do this in calories, we could take the 79 calories per gram and multiply it by 2,000 grams. And then we would have the value for the latent heat in calories. So that is another way we could do this problem, which would be more like a chemistry calculation, but it would be equivalent. By the way, the kind of calories that we're talking about here, where 4.18 joules equals 1 calorie, are not the kind of calories you count, okay, when you're going on a diet. Those are kcals. Okay? And so these kind of calories are just 1,000th of the kind of calories that you count. And so we don't want to confuse those two. Okay, so what this has shown us then is that we have a certain amount of heat that's required for a phase change, but we also have heat that's required for a temperature change. Okay, so if I give it this amount of joules, I've turned it into water. So let's go one more step with this. Now that it's water, let's turn it into 10 degrees centigrade water. Well, that's going to require more heat, but now that we've changed it from a solid into a liquid, we can now just add to that temperature. So that gives us Q equals M. Okay, so that's 2 kilograms times C, that's 4,190 joules per kilogram degrees centigrade, times the change in temperature, which is 10 degrees centigrade minus 0 degrees centigrade. Okay, and so that's going to be 20 times 4,190. And so that gives us 8.38 times 10 to the 4. Joules. So that's the heat required then to take it from 0 to 10. So if we're looking at a plot then of the temperature versus the heat that's added, we start out at 0. And so here the amount of heat that we add is going to be 6.62 times 10 to the 5 to get it to here. And then we're going to go from 0 to 10. And this amount of heat is going to be 8.38 times 10 to the 4 joules. And so Q total then, to melt the ice and then bring it to 10 degrees centigrade, is going to be the sum of those two, which is 7.45 times 10 to the 5. So that's equal to the Q ice plus the Q water. Or this is the Q water to change the temperature of the water. This is the Q to melt the ice. Okay, so Q total then is just the sum of those two. Now, what if we had raised this all the way to 100 and then we wanted to evaporate that water? Well, if that's the case, then we also need the latent heat of vaporization for water. So that's equal to 549 calories per gram times, again, 4.19 joules per calorie times 10 to the 3 grams per kilogram. So that's 4190 times 5. Actually, this is 540. Sorry. 2.26 times 10 to the 6. Joules per kilogram. Okay, so if we wanted to take this water, let's say the water was at 100 degrees centigrade. It's 2 kilograms now of water at 100 degrees centigrade. Let's find the heat to turn it into steam. Well, that's just going to equal the mass of the water at 100 degrees centigrade times the latent heat of vaporization for water. That's our LV value. Okay, and so that'll be equal to 2 times this is 2 kilograms. Times 2.26 times 10 to the 6 joules per kilogram. So again, the kilograms units cancel out. And so then it'll just be double 2.26, which is 4.52 times 10 to the 6 joules. Okay. Let's compare that with the Q ice that we looked at before. The Q ice was 6.62 times 10 to the 5. This is 4.52 times 10 to the 6. So this is something like 8 times as much heat as was required to turn it from a solid to a liquid that it takes to turn it from a liquid to a gas. So if we were to go all the way to 100 here, and I haven't calculated how much total energy it would take to bring it to 100, it would be something like 10 times this value, okay, or 8.38 times 10 to the 5. I'll leave that as an exercise for you to show that that's what it would be to bring it to there. Then the Q to turn it into a gas here would be 8 times this amount, 7 or 8 times, and so that would be our 4.52 times 10 to the 6 joules. And so this isn't even to scale. I would go all the way off the board if I were going to try to draw that to scale. And it takes way, way more energy to evaporate water than it does to turn it from a solid to a liquid. Why? Well, because water is a polar molecule. And so that means that it's got a positive and a negative end that even in the liquid state creates a pretty strong bond. And so you haven't broken that bond completely when you just broken it from the hexagonal form of the solid state into the liquid state. As a matter of fact, the molecules are even closer together, which means that those attractive bonds are still quite present. And so, but to rip them apart and to get those molecules so that they're really far away from each other takes a lot of energy. And so that's what the reason why it's so difficult to evaporate water. On the other hand, if you took some alcohol and spilt it on the table, it would evaporate right away. And everybody in the whole room would smell it, right away. And that's because alcohol doesn't have a strong molecular polar tendency to hold the molecules together in the liquid state. So its latent heat of vaporization would be small. Whereas for the polar molecule water, the heat of vaporization is very large.